Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to go through section 5.5, counting techniques. I'm also going to say, going into this is probably my favorite section in 5.5, and most students tend to agree with that, particularly because, like section 4.4, it's the easier of the sections for this entire chapter. We're going to have here what is called the multiplication rule of counting, which is going to allow us to find how we calculate how many ways something can happen. For example, say I have 5 light switches. If you consider maybe your house has a little box next to a door that has 5 light switches on it, or even in a classroom with 5 light switches. What I want to consider is how many different ways I could have these light switches in order, like how many ways I could have some of them being on and some of them being off. Well, in order to do that, I'm going to look at each light switch and consider how many options it has. The first light switch has 2 options. The second light switch also has 2 options. All of these light switches have 2 options, either being on or being off. Well, in order to find how many ways I could have these in order, the easiest way I could do that is simply multiplying. If I do 2 times 2, that's 4, times 2 is 8, times 2 is 16, times 2 is 32. There are 32 ways I could have light switches being on and off if I have 5 of them. That's the multiplication rule of counting. It says if there are P selections for the first choice, Q for the second, R for the third, just to represent with variables, then the number of selections for all choices is done by doing P times Q times R times whatever else you have. That's how many ways you could have selections for objects. So let's go into a couple examples of this. I always like to do this with boxes, by the way. It's a nice way to start with it. 3 members from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. So we have 3 different positions to fill: chair, vice chair, and secretary. Chair, vice chair, and secretary. The first person selected is chair, second is vice chair, third is the secretary, and how many different committee structures are possible? Well, for the chairperson, we have 14 different people we could select for the chairperson. Once the chairperson is selected, I have 13 different people I could select for the vice chair. Once the vice chair is selected, I have 12 people I could select for the secretary. In this case, unlike the previous example with the light switches, once one thing has been selected, it cannot be selected again. I cannot have one person hold multiple positions. It even says the first person is the chair, the second is the vice chair, etc. They are different people. Therefore, in order to find how many ways I could have a committee structure, I simply multiply these together. I get 14 times 13 times 12, and I end up with 2,184 different possibilities for just selecting 3 people out of a group of 14. That is a lot, and that's kind of astounding, honestly. You do not want to list all the different possibilities there are. Let's do another one. Outside of a garage, there's a 10-digit keypad numbered 0 through 9. The correct 4-digit code will open the garage door. So I need to have 4 digits here: 1, 2, 3, and 4. The numbers on the keypad can be repeated, meaning we can use a number more than once. How many codes are possible? And then also the probability of getting the correct code. Well, the first digit I could select, 0 through 9, I could select any of the 10 possible digits. Since it says a digit can be repeated, I could then select any of the 10 digits for the second number, and the third, and the fourth. If I multiply these together, 10 times 10 times 10 times 10, what I get is 10,000. There are 10,000 different possibilities for just a 4-digit keypad. Therefore, the probability of getting the correct code on the first try, where there's only one correct code, would simply be 1 out of 10,000. Which is incredibly unlikely. That'd be 0.0001. So a very unlikely chance of randomly guessing the correct code. Now, this is not considering things like bias in terms of people maybe selecting their birthday or an important date to them. This is just selecting in a vacuum. What's the probability of just randomly selecting the right 4-digit code? So that's the multiplication rule of counting. Nice and easy. Now, with the multiplication rule of counting, we're going to have a lot of patterns show up. If you notice with the committee structure before, we did 14 times 13 times 12, and if I continued on in this fashion, I would keep multiplying each integer below that. So times 11, times 10, times 9, etc. This kind of operation is done very often, and because it's done very often, there is mathematical shorthand for that. The mathematical shorthand is known as a factorial. This is where I say math gets exciting, because a factorial is represented with an exclamation point. Therefore, you start to read numbers instead of a number like what we have down here of 4 exclamation point. I would now read this as 4 because it has an exclamation point, so it's exciting. In order to do these, that exclamation point literally means take that whole number and multiply it by every whole number below it. So 4 factorial means 4 times 3 times 2 times 1. We continue until we hit 1. We do not go further and hit 0 because then that would nullify everything. 4 times 3 is 12, times 2 is 24, and times 1 is still 24. So that's 4 factorial. 12 factorial would follow along the same pattern. 12 factorial would be 12 times 11 times 10 times all the numbers down until you hit 1. Now that gets kind of tedious because that you'd be typing in 12 different numbers with multiplication signs in the middle, and that gets kind of long. There is actually a factorial operation in your calculator, and I'm going to show you how to do it. First, type in the number 12. You want to type in the number that you're going to apply a factorial to first, just like how we write it. We would write the number 12 first before I write the exclamation point. Once I have the number 12 typed in, then I'm going to go get the factorial operation, which is located in the math section. So hit math, which is right below alpha. You may remember this back from chapter 1. And like chapter 1, we're going to go over to the probability tab. The probability tab is where we did random integers, and you'll also notice right above random integers is the factorial button on number 4. If we hit enter on that, that will paste it to the main screen. We now have 12 factorial, and if I hit enter, we get what 12 factorial equals, which is a really large number, 479,001,600. That's a lot. That's a huge number. Okay. Now a couple examples of factorials. You've just been hired as a book representative for Pearson Education. On your first day, you must travel to 5 schools and introduce yourself. How many different routes are possible? Well, when going to these 5 schools, I could go to any of the 5 schools first. Once I've gone to that school, I could then go to any of the other 4. Once I've gone to those 2, I could go to any of the other 3, then the other 2, and then I only have 1 possibility. So this is 5 factorial. You could do 5 factorial since we did 4 factorial before and multiply that by 5. Or in your calculator, we could do 5 and then go hit math and go find the factorial button in the probability tab. So 5 factorial should give us a 120. While playing Scrabble, you had the letters A, E, I, S, D, P, L, R. So that's 8 characters. How many letter combinations can you create? Now we're not considering if they create actual words, we're just combining how you would order these 8 letters. Therefore, that's going to be 8 times 7 times 6, or 8 factorial. If we do 8 factorial in your calculator, I believe you should get 40,320 if memory serves. Yep. Okay. So 8 factorial is 40,320. Think about that the next time you play Scrabble. You have 8 characters. Think about how many different ways you could order those 8 characters. Just maneuver things around. It's a lot. Okay, so far that's how you would deal with counting. However, if you remember as well, the first situation we did, I keep harkening back to this, the first situation we did with the 14 committee members, this wasn't a full factorial. This was basically what we would say is a truncated factorial. We did the factorial process, but we stopped somewhere. We did 14 times 13 times 12, but I did not continue past that. And that was because I didn't want to order all 14 members. I only wanted to order a selected number of them. That itself has a special name. That is called a permutation. A permutation is an ordered arrangement of objects, and typically is an ordered arrangement of some of the possible objects. A couple things about permutations. A permutation has n objects that are distinct from one another, so people that are different from one another, or letters like in the Scrabble example. Repetition of objects is not allowed, so you cannot have something like the gate code we did before. You cannot reuse an object once it has been used. And, most importantly, order is important. That's the most important line for permutations. Order is important. Like with the committee structure, when I selected the president, vice president, secretary, whoever was selected first for the president, that mattered. So the first person selected got a different treatment than the person that was selected second or the person that was selected third. You can also consider this like a race. Whoever wins first gets gold. Whoever wins second gets silver. That means that there's different treatment to whoever gets first, second, third, fourth, etc. And we have the formula here, and I'll go through it real quick. So this is read as NPR, where N is going to be your sample size, and R is going to be the number selected. Therefore, for the committee structure, we had 14 people, and we chose 3 of them for positions. So I would write this down as 14 individuals permutate 3 of them. 14 was my sample size, 3 is how many I selected. If I do this formula, what this is n factorial, or in this case 14 factorial, divided by 14 minus 3 factorial. Well, if you remember, 14 factorial means 14 times 13 times 12 times 11 times 10 times etc. etc. 14 minus 3 is 11, and 11 factorial means 11 times 10 times etc. etc. The way I wrote this fraction was very particular because if you notice now, I have an 11 on top and the bottom, and I can eliminate those. Same thing with 10 and 9 and 8, etc., etc. All of these numbers will eliminate except for 14, 13, and 12. And that is how we solve that first problem. We did 14 times 13 times 12. So basically showing that it gives you the same answer. I wanted to show that with a solution that we had already done to show that how permutation works. Now there is going to be a calculator function for permutation, so we won't need to do it by hand here, but I wanted to show you where it comes from and how it functions. But before we get into some examples of that, we also want to talk about what is called a combination. A combination is where you have a collection of objects with no regard to order. So, just like permutations, the n objects you have are distinct from one another, and the repetition of objects is not allowed, so you cannot use an object again. But unlike a permutation, the order of your objects is not important. Therefore, this would be like making a committee structure where they don't get different positions. They're just selected to work together. So if I was selecting 3 people out of 14 to work together, and they were not given positions like president, vice president, and secretary, that means the order I selected them does not matter. In that case, we need to combine multiple different orderings that all use the same objects. For example, if I have three people A, B, C, those three people could be ordered in a lot of different ways. I could also have this as BAC, that's the same three individuals, or BCA, that's the same three individuals, or ACB, or CAB, or CBA. That's 6 different ways I could order 3 different individuals. Now, for permutation, these would all be considered different because they would be given different treatment. The first person selected would be president, second vice president, third secretary. But with a combination, all of these would be considered the same. Therefore, they would be combined into one. So this would be considered one combination. So a combination is going to take the possibilities of permutations and reduce it down so that there's no repetition of individuals selected or groups. You'll always have a smaller amount of combinations than you will permutations for any situation. Again, the formula is given there as well, and you'll notice that there's a additional thing on the denominator, so an additional value of r factorial. That means the denominator is going to get smaller, therefore the overall value will, or the denominator will get larger, therefore the overall value will become smaller. Now, like permutations, we're going to be able to do that in our calculator, and we're going to go through some examples of these. For each of these, our first goal is going to be to try to identify if it's a permutation or a combination, and then we'll deal with it from there. How many ways can 3 different students from a class of 10 be assigned to work the 3 homework problems on the board? Student 1 works the first problem, student 2 works the second, student 3 works the third. Now, based on that last sentence, since they're working different problems, that means they are receiving different treatment. Therefore, this is a permutation. Since it is a permutation, we then need to consider what the sample size is and what the amount of selections are. In this case, it says that this is selecting from a class of 10 individuals, so I have 10 students overall, and of those 10 students, I am selecting 3 to work problems on the board. So this is going to be 10 permutate 3, as we would read. In order to do this in our calculator, like with the factorial, what we're going to do is type it in as I wrote it here, meaning that I'm going to type in the number 10 first before I go find the permutation function. Let's do that. I'll type in the number 10 first, and then we'll go find the permutation function. Permutation function is going to be in the same place as the factorial. So we're going to hit Math. We're going to go over to the Probability tab. And then you'll see on number 2 and number 3 the permutation and combination functions. In this case, we want a permutation, so I'll hit NPR, which is number 2, and that will paste to the main screen. Now, some functions format like this, where we'll say 10 NPR, and then you would like to type in 3 to indicate what R is. However, some more advanced calculators, like the TI-84 plus CE, will format it in the way that I have it written on the page here, where you'll type in 10, and then you'll go get NPR, which will put 10 as a pre-subscript. Either way you do it, though, is perfectly fine. And what we get is an answer of 720. And that would be our answer. Now, just as a test to show you that combinations would have far less options, if we did this as a combination instead where the order did not matter, if I did 10 and then I do a combination on this, so 10 combination of 3, the same values, I get instead of 720, I get only 120. So there's 600 less options if the order does not matter. That's a significant difference. And it'll only change the more and more options there are. Alright, so let's go through a lot more examples here. I'm going to do these ones here, and then I'm going to ask that you do the ones on page 18 on your own. So let's do, how many ways can a focus group of 5 consumers be selected from a list of 25 people who purchase a particular product? Well, in this case, I don't have any indication given to me that the individuals selected are getting any different treatment. They're all just being interviewed, or they're being put into a focus group for this product. Therefore, because there is no indication of order, we are going to consider this a combination. And it's going to be a combination where we select 20 of the 25 people, we're going to take 5 of them. Sometimes this is even read as 25 choose 5. Now to run this, in our calculator we hit 25 first, go get math, go over to the probability tab, and we want the function for combinations. So 25 NCR, and we are selecting 5. That will give us 53,130. So that's how many ways we can select 5 people from a list of 25. A lot more than people would maybe think at the beginning. Lastly, a group of 4 friends, Alan, Becky, Curtis, and Dylan, are going to play volleyball by dividing into 2 teams. How many different groups of the 4 friends taken 2 at a time are there? Well, again, there's no indication that it matters in terms of the order that they are selected. It doesn't say the first person selected is the captain and the second person is not the captain or something like that. So since there is no indication of order, this is going to be another combination. In this case, looking at that last sentence, it says, of the 4 friends taken 2 at a time, therefore we are taking a total of 4 people and we're choosing 2 of them. If we do this in our calculator, that'll be 4 math, go to the probability tab, and select NCR. 4 NCR and 2 should give us an answer of 6. So there's 6 different ways of having groups of 2 teams with those 4 people. Alright, hopefully you're starting to see how order matters or if it doesn't, and then plugging those into the appropriate situations. Again, I recommend that this page 18, you try this on your own, so pause the video now and see if you can solve these 5 problems on your own. They shouldn't take too much time, but when you have them done, go ahead and unpause the video and see how you did. Okay, that's enough time. So hopefully you had already paused and tried these problems on your own. First one says, suppose 24 speed skaters are competing in the Olympics. How many ways can the top 3 racers finish the race? Since it says the top 3 racers, that means that this is going to have order there. The top person will get gold, second, silver, etc. So since order matters, this is a permutation. This is a permutation of 24 individuals where we are selecting 3 of them. So in our calculator, that's going to be 24 math over in probability, and then we use the NPR function with 3 people. 24 permutate 3 will give us an answer of 12,144. Second question. An instructor of statistics class of 25 students would like to take a simple random sample of 3 students for a survey. How many different samples are there? Since it just says it's a survey, doesn't say anything about any indicated order, this is a combination. We are taking 25 individuals and we are choosing 3 of them. So this is going to be 25 math probability NCR of 3. Enter. We get an answer of 2,300. I'm going a little faster with these because I'm hoping that you had paused the video and tried these on your own first. And because they don't take too much time themselves. 3. 4 members from a 20-person committee are to be selected randomly to serve as chairperson, vice chair, secretary, and treasurer. At this point, we already know that order matters. This is like the first problem we did in this section. So order already matters. We know this is going to be a permutation. Of the 20 people selected, we are selecting 4 to fill those positions: chair, vice chair, secretary, and treasurer. So this is going to be 20 permutate 4. 20 math probability permutate function. So 20 NPR 4, and we get 116,280. Next one, we get a lottery exists where balls numbered 1 through 25 are placed in an urn. To win, you must match the first 4 balls chosen in correct order. How many possible outcomes are there for this game? Well, it says that they need to be in select order. That's pretty on the nose, so we know that order matters. Therefore, this is a permutation. We are selecting, of the 25 possible options of the balls numbers 1 through 25, we are selecting 4 of them. So this is going to be 25 math probability NPR of 4. We get an answer of 303,600. Lastly, ping pong balls in a bin are numbered 1 through 99. 3 balls are to be drawn from the bin sequentially. If a lottery tickets holder numbers exactly match the numbers on the ping pong balls in any order, he or she is the winner. Since we know that this is in any order, then we can solve this by doing a combination. We are selecting, of the 99 balls, we are selecting 3 of them. So it's going to be 99 math probability NCR. 99, choose 3. And we get 156,849. For both of them, they also ask for the probability of getting the correct numbers. That would simply be 1 out of each of these values. So 1 out of the 303,000 and 1 out of the 156,000. All right, so that's how you would solve for some permutation and combination problems. On the next couple of pages, we have some special cases. At this point, we've been dealing with distinct items that are different from one another. So ping pong balls that are different numbers, or individuals that are different numbers, etc. But if we have non-distinct items that are not different from one another really, then we have different formulas for that. This is like if I was selecting from balls in or marbles in a bag, and I had 4 blue marbles in there that are not distinct from one another. That would be an example of non-distinct items. Now to do that, what we have is this formula on top, or this formula here. The top n factorial, that's going to be the total sample size. So how many total objects we are working with. On the bottom, we have a lot of factorials that are multiplied by another. The first factorial, n sub 1 factorial, that's going to be for the first, or the number of objects for the first non-distinct item. Then n2 factorial is going to be the number of objects for the second non-distinct item, and on and on and on. A good trick for this is to note that n factorial on top is the total, and then when you sum all the factorials on the bottom, that should equal the factorial on top. You'll see what I mean in just a moment. Here we have how many different vertical arrangements are there of 10 flags. So we have 10 flags overall, 5 of which are white, 3 are blue, and 2 are red. So these are non-distinct items because I have 5 white flags, all of which are not really distinct from one another. One white flag is really the same as another one. Therefore, in order to solve this, we have on top the total amount of items, which is 10 factorial. And on the bottom, we have a factorial for each non-distinct item. For white flags, there are 5 of them, so 5 factorial. For blue flags, there are 3 of those, so 3 factorial. And for red flags, there are 2 of those, so 2 factorial. What I meant before for adding numbers together, if you notice 5 plus 3 plus 2, that equals 10. So the numbers on the bottom should sum up to the numbers on top. If not, you're probably missing something. All right. So on the bottom, we've actually done these before. 5 factorial we had done before. That was 120. 3 factorial is 6. That's just 3 times 2 times 1. And 2 factorial is 2. It's 2 times 1. 10 factorial I don't necessarily know off the top of my head, though, so we can do that in our calculator. 10 math probability, and we run the factorial. That will give us 362,8800. So 3,628,800. Therefore, I can solve this by taking that number and dividing by those numbers on the bottom. So dividing by 120 times 6 times 2. Note that I put those in parentheses because I just wanted to do it now instead of separately doing 120 times 6 times 2 and then dividing those two values. What we get is a final answer of 2,520 ways of ordering these 10 flags. You also want to make sure that your final answer here comes out to be a whole number. If it does not come out to be a whole number, check the factorials that you set up. You probably set up one of them incorrectly, and the numbers on the bottom don't add up to the numbers on top. It should always come out to be a whole number. Let's do another one. How many distinct arrangements can be formed from all letters of the word statistics? Well, if you notice, the letters in the word statistics, some of them are repeated. So let's go through those. First, we have the letter S. There's 1, 2, 3 S's in the word statistics. Then we have the letter T. There's also 1, 2, 3 T's in statistics. A. In this case, there's only a single A in statistics. And we continue to do this for all letters. There's also I's. There's also C's. For I's, I see 1, 2 I's. I also see a single C. If we also count the letters here, statistics has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. And if I add all these up, that does add up to 10. So we have everything counted. Therefore, this is going to look like 10 factorial, the total amount of letters, over 3 factorial times 3 factorial times 1 factorial times 2 factorial times 1 factorial. Now we got 10 factorial before. We solved that. It's still on my calculator over there. 3,628,800. And on the bottom, 3 factorial is 6 times another 6. 1 factorial is 1. 2 factorial is 2. And 1 factorial is 1. So this is that 3 million number. Over 6 times 6 is 32. Times 1 is 32. 6 times 6 is 36. Times 1 is 36. Times 2 is 72. Times 1 is still 72. So we have 3,628,800 divided by 72. That gives us a final answer of 50,400. Again, this formula is not, there's no quick way in the calculator to do this one, not necessarily, but this formula is available to you on your formula sheet, so you will not need to memorize it. Just make sure you know where to find it. Okay, we got one more page here. Yes, page 20. This is for how to deal with probability. Now, using combinations can help us solve for really complicated probabilities that we weren't otherwise able to solve before. And remember that probability in general is how many ways something can happen over the total number of possible outcomes. And what we've been talking about in section 5.5 is how to calculate how many ways something can occur. So we can use that general probability and concepts of combinations to solve for probabilities that would have otherwise been very complicated to do. For example, a management training seminar in a company requires selecting 5 individuals randomly from a pool of 9 administrative assistants and 5 administrators. First, what is the probability that they will all be administrative assistants? Well, we can do this by doing a lot of multiplications and considering dependent probabilities and um, and combinations and values like that. We can do a lot of multiplications of fractions, or we can do this with combinations. The way we want to do this is first looking at the denominator. On the denominator, we want to see how many different possible outcomes there could be. Well, overall, we are selecting 5 individuals. We are selecting 5 individuals from a pool of 14 total people. Therefore, the number of possible outcomes on the bottom should be how many ways I can select 5 people out of 14 total. I don't have any indication here that order matters, therefore this is going to be a combination where I select 14 people and of 14 people I'm selecting 5. On top, I'm going to say how many ways I can have all administrative assistants. To focus on that further, all administrative assistants means that I have 5 administrative assistants and 0 administrators. I am going to do both of those. And notice that I use the word "and" in the middle. That means I'm going to be multiplying. On the top, I'm going to have one combination for how many ways I could select administrative assistants. Well, of the 9 possible administrative assistants, I want to select any 5 of those. And of the 5 administrators, I want to select none of those. So 5 choose 0. Now you may be asking, why do I need that second combination when I'm not selecting any administrators anyway? And even if you do 5 choose 0, you will get an answer of 1 for that. The reason I do that is because it will add more consistency for the later couple problems, particularly the last one that we have for this example. Alright, so we can solve for each of these. So we could do 9 math, probability, NCR. We could do 9 choose 5. And what we get is 126. If you do 5 choose 0 in your calculator, you will get an answer of 1. It's basically asking how many ways can you choose nobody, which is only one way. But we also need the bottom, which is 14 choose 5. So 14 NCR of 5. And we get 2002. So overall, we get an answer of 126 out of 2002. That would be our final answer. All right. Now again, you could do this with dependent situations and conditional probabilities, but this can help solve for some more complicated ones. These first two you could probably just do directly with a lot of fraction multiplication, but the third one definitely would be more complicated. Second one says, what is the probability that they will all be administrators? All right, well, like before, on the bottom, I'm going to say how many ways I can select 5 people overall of the total pool of 14. And then on the top, I'm going to indicate a combination for how many administrative assistants are selected and how many administrators. Of the 9 administrative assistants, I want to take none of them. And of the 5 administrators, I want to select 5 of them. If I solve these, 9 choose 0, that will give you 1, just like 5 choose 0 gave you 1. And also, 5 choose 5 will also give you 1. If you do 5 choose 5 in your calculator, you will get an answer of 1. Reason is, the only way of selecting 5 people out of 5 is one way. You can only select all of them. And on the bottom, we get 2002 again, which is what we solved before. So this will give us a fraction of 1 out of 2002. Lastly, what is the probability of selecting 2 administrative assistants and 3 administrators? Okay, now this is starting to split up things. Overall, we are still selecting 5 individuals though. So 14 choose 5 on the bottom. On top, we have a combination for how many administrative assistants are chosen. Of the 9 administrative assistants, I want to select 2 of them. So 9 choose 2. Of the 5 administrators, I want to select 3 of them. So 5 choose 3. On the bottom, we have 14 choose 5. That's 2002. On the top, you have 9 choose 2. That should give you 36. We'll show that here. 9 choose 2 should give you 36. And 5 choose 3 should give you 10. So let's do that one. So 5 choose 3 should give you 10. Overall, that means we have 36 times 10 is 360 out of 2002. All right, now we noted before with the non-distinct items there was a pattern that can help you make sure that you do this correctly, and we have a similar pattern here as well. For the non-distinct items, we wanted to make sure that the numbers on the bottom add up to the number on top. We have the same thing here. If you notice, the first number in each combination, 9 and 5 on top. 9 and 5 add up to the total amount of individuals of 14. So those should all add up to each other. Likewise, the second numbers, 5 and 0, add up to 5, which is the second number on the bottom for the combination. So that connection can help you make sure that you set up your combinations correctly. We see that as well for the last problem we did. 9 and 5 adds up to 14, so all that checks out. And then for the second numbers, 2 and 3 adds up to 5. So there's always that connection that can help you make sure that you set up your combinations correctly. Now these are a little bit complicated, so I want to do at least one more of them. Suppose a compact disc you just purchased has 17 tracks. After listening to the CD, you decide that you like 6 of the songs. This should sound familiar to a previous problem we did in an earlier section. The random feature on your player will play each of the 17 songs once in random order. Find the probability that among the first 5 songs played, you like 2 of them. Now remember, if we did this directly, we would have to consider all the different ways I could have 2 songs out of 5 that I like. Instead, we could do this with combinations. Overall, there are 17 songs, and I'm playing 5 of them. So on the denominator of my overall fraction, I'm going to have 17 choose 5. On top, I'm going to have 2 combinations. I'm going to have how many that I like and how many that I dislike. The first combination will be how many songs I like. It says that I like 6 songs. So of the 6 songs that I like, I want to play 2 of them. So I'll have 6 choose 2. Of the songs that I dislike, which if I like 6 songs, that means I dislike 11 of them, of the 17. Of the 11 songs I dislike, I want to play any 4 of them. Okay, so now we have all of our combinations and we can solve for these. The bottom one is going to show up in all these cases, so we're going to want that anyway. 17, choose 5. 6,188. If we do 6 choose 2, that should give us 15, I think. Yeah. 6, probability, NCR, choose 2, should give us 15. And then if we do 11, choose 4, I think that gives us like 330 or something. Okay, cool. 330. Multiply those appropriately. And we get 15 times 330 gives us 4,950. Next, you like 3 of them. Well, on the bottom, I'm still playing 5 songs, so 17 choose 5, and that will also be true for the last problem we have here, so let's go ahead and set that up. But on top, I had to split that into how many I like and how many I dislike. The first combination is how many I like. Of the 6, I want to play 3 songs that I like. And that means of the 11 songs I dislike, I'm going to play any 2 of them. 17 choose 5 we did before was 6,188. If you do 6 choose 3, that should give you 20. And 11 choose 2 should give you 55. We can check both of those. 6 math probability of 3 should give you 20. And then if you do 11 choose 2, you get 55. Okay. For those wondering, when you do enough combinations, you start to remember how to do the multiplications and divisions in your head for the original formula. So it's not anything special. Okay, so if we do 20 times 55, we get 1,100. 20 times 55. Yeah, okay. All right, notice in all of these, we've been keeping those same patterns that we've been identifying. The second numbers always add up to each other. 3, 2, 5, 2, 4. Whoop. That means that there's an error. Okay, so sorry about that. There actually was an error up here. But that's why we check. So this should not have been 330. This should not have been 4. This should be 3. Of the 2 songs that of the 5 songs I played, 2 I like, 3 I dislike. I apologize for that. So 11 choose 3, we need to fix that. So 11 choose 3, we get 165. So 165 times 15, and that gives us 2,475. I apologize for that error. But that's why we check it, right? We want to check to make sure that everything aligns correctly. 2, 3, and 5, 3, 2, and 5. Same thing with the first number for each of these. 6, 11, and 17 add up to each other, or 6, 11 adds up to 17. So all of that makes sense. Okay, easy way to check yourself, just like I did there. Lastly, you like all 5 songs, so that means of the 6 songs I like, I play 5 of those. And of the 11 songs I dislike, I play none of those. Again, check. 6, 11 adds up to 17, so that's still good. And 5, 0 adds up to 5. So that's all good. Solve for these. If you do 6 choose 5, you will get an answer of 6. And if you do 11 choose 0, you'll get an answer of 1 over our familiar number of 6,188. But let's check that. We already know anything choose 0 is 1. We've done a few of those. But 6 choose 5 should give you 3. Or 6 rather, yeah. So we get 6 out of 6,188. So those are a bit complicated, and as you saw, I made a quick error. I think I got 4 from thinking about taking 2 out of 6, and that's where I got 4 from. But it's very easy to check yourself with these numbers because for the combinations, they should add up to each other. Note as well that even if a combination is empty, like this number that I have here for 11, choose 0, I still want to indicate that. That way it's easy for me to check to make sure everything is in order. With that said, that's everything in Section 5.5 and Chapter 5 in general. So at this point, you should be able to go through and complete all the homework for Chapter 5. If you have any questions, feel free to put those in the comments below or ask your instructor directly. With that said, I hope you have a nice day.